Hello everyone. This is my final project report presentation for Data 259 final project. And I did a further investigation on gender and race versus income, how gender and race would influence income. And here is the data source. It's from Kaggle, and then here's the link. And then this data basically have a similar structure, um, like just like the income CSV we use for past assignments, but I'm sure that is a totally different data set. So here are steps for data cleaning, including dropping missing values and remove capital gain and capital loss columns, which are basically irrelevant to this study, and also and then it results in this size of a data. And for the first step to study this data, I would like to just check whether this is a good representation of the population, which is the United States citizens. So by doing that, I basically created a confidence interval for the income greater than or equal to 50K proportion, as well as the proportion of work class that is privately working. And here are the 95% confidence interval generated. And it's actually pretty close to the actual number. Even though this is like a number from 2019, but it's very interesting. And then I run a least square regression on this data set, trying to explain it. However, there's like a multicollinearity problem that I run into. Also, um, we have to always check for whether these p-values they can actually explain this problem or not. So I basically use Hom-Bonferroni correction and FDR correction in this process. So for Hom-Bonferroni, the p-values doesn't really change. However, for the FDR, it basically says that none of the variables can be used to explain the relationship between these variables, gender, race, age, and stuff. Um, between these variables and the final variable, which is the income. And the conclusion is that FDR is a much stricter correction method. And then I run some visualizations about the variables themselves. As you can see, there is like an outlier problem generating in numerical data especially. So then I chose to shrink the size of the data using this z-score greater than or equal to 3 method. And then based on the shrunk data, I run machine learning models of them. So here are the models that are used: gradient boosting, AdaBoost, as well as logistic regression. And then I run some fairness analysis on them. So first of all, you can see that the disparate impact of all of the three models is like really high. They're 3.3, much greater than 1, meaning that for gender especially, the sample are way more stressed than the female samples. And it is very interesting to see that in the graph as well as in the AdaBoost disparate impact for race. AdaBoost appears to be a really conservative model in the sense that it really does not stress true positive. It really only focuses on true positive rates of the results. However, it basically ignore some other aspects of this data. Here is like summary for the above visualization. And this is when I apply some fairness metrics on this data. As you can see that all of the equalized odds difference metric fell because it's a really stricter metric. It looks at the both side of the problem, while equal opportunity difference only looks on the true positive rates of things. So for the value, if they're closer to 1, meaning that um, it is a fair problem. It means that if the number is closer to 1, closer to 0, there's a smaller gap between different populations. And I would like to discuss how in the above chart things are happening. So it really, apart from the hardness to pass equalize odds metrics. So it also suggests that while positive outcomes are reasonably fair, error rates, which is the false positive and false negatives, are not equally distributed across groups. And the bias is more pronounced than equalized odds, indicating a need for more refinement to reduce disparities in error rates. And then I did a black box fairness matrix analysis on this. So it basically generates three key insights. The first is that there's a superior gender equity, in comparison. And then there's an improved parity in race. Also, there's a balanced error rates. So in the quite opposite, I can say that there's actually income disparities exists across gender and race because while you're working in a black box model, it does not have any assumption assuming that everyone's equal, and that generates a way less, as you can see, superior gender equity as well as improved parity in race. So that basically tells the problem. And then I was also interested in looking into chi-square tests, whether it can show demonstrate some insights for this relationship, or like in the sense of association or not. Also, I compared Fairlean results with the fairness matrix results from the previous three models, and you guys can look into that. And because of the shorter time of this presentation, I will have to end here. But I would like to draw some conclusion here. And except for income disparity actually exists across gender and race, I would like also to say that models demonstrate varying levels of bias, and fairness metrics are crucial for identifying these issues. And addressing bias in machine learning really requires careful pre-processing as well as model selection and fairness evaluations.